All right, welcome back. So we're taking a little bit of a detour from the book. So the book talks about surface integration by doing parameterization. That's not what we're going to be doing on Canvas. I've already uploaded the document that kind of goes through surface integration that we're going to be talking about today. So just another resource for you. But we are going to talk about it in class. So here is surface integration. Suppose we now want to calculate the surface area of some surface given by some function g of x, y, z is equal to some constant. So the idea here is imagine that we have our XYZ plane or coordinate system. And I have some surface here. And this has a projection onto any plane. So here we've shown the XY plane. To approximate this, right, because that's how we've been doing all of this integration, is let's take a small plane, small segment here, and we're going to project it down onto this plane. And once we do this projection, we're going to try to find the area of this thing. And then we're going to add up all of this. But there is a difference between the flat area here and this curved area, surface area up on here. So we need to kind of figure out the transformation for that. Now this is just like this coordinate transformations that we've been doing before. Although once we kind of figure it out, it's just going to be a routine for us to kind of figure out the surface area to an area. So the goal is to project some small surface area onto one of the coordinate planes. So this involves some transformation. The transformation that we're going to be using is that we'll have some d capital S. Okay, so instead of just d lowercase s for arc length, typically d capital S denotes some small surface area component. So some small surface area will be the magnitude of the gradient of g, and then the gradient of g dotted with this p vector. We'll talk about that in magnitude dA. So if our function is given by this g function here, Then the translation from ds to dA is the magnitude of the gradient of g over the magnitude of the gradient of g dotted with this p vector. This p vector just denotes the direction at which we're projecting. So in this case, because we're projecting to the xy plane, we would use k hat, right? If we were projecting to the xz plane, we would use j hat. And if we were projecting to the yz plane, we would use I hat. And it doesn't matter if you use the negative or not here, because we're looking at the magnitude. So in general, the surface integral is related by so imagine that we have some double integral that is the surface area. So we'll use a S here of some function of x, y, and z. We have some small ds component here. So this is a capital S for surface area. We can relate this to a double integral of f of x, y, and z. We translate ds to dA. And this area integral is over some region R. This R region is the projection of our surface area onto that same coordinate plane. So a little more detail here. If this is our surface S, this is our region R. So there's a few steps that we should kind of follow when we're doing these surface area integrals. 1, we're going to choose the coordinate plane that we project our surface to. This defines the p vector. Determine the projection region R. Find out what the surface area looks like once you project it to that coordinate plane. Step 3, compute the magnitudes of the gradient of g and the magnitude of the dot product between the gradient of g and that p vector. So step 4 is that because we have this function g of x, y, and z is equal to c, we can use it to reduce the integrand where needed. And what I mean by that, if you look back up here, these are double integrals, but our integrands have an x, or possibly have an x, y, or a z in them, right? So our area integral, once we translate this, might have, it be in the xy plane. So we do a dx dy in no particular order. If we have a z that's in here, it doesn't make sense for this integration. However, we can replace z by using this g function. And then 5 is evaluate the regular area integral over R. So just as a note, if we wanted to just find the surface area of some region, we could just do the surface integral over an integrand of 1 for that corresponding surface. So just like if you want to know the area of a region, you have an integrand of 1. Here, if you have an integrand of 1 for a surface area integral, it will just give you the surface area of that region. Okay, so let's do an example. So we're going to find the surface area of the plane 3x plus 2y plus z is equal to 6. That lies in the first octane. So we have that x, y, and z are all non-negative. Okay, so we look at this function. This is a function of x, y, and z on the left-hand side is equal to some constant, so it's perfectly a candidate for our g. So we have that g of x, y, and z is 3x plus 2y plus z. It's also equal to 6. So we can take a look at this constraint possibly later for step 4. So step 1. This is a plane equation. So it's really easy to project to any of the coordinate planes. So for this case, we're just going to choose the xy plane. But maybe if you want some practice, you can redo this for a different coordinate plane so you get the same answer. So because we're projecting to the xy plane, our projection is going in the z direction. So we choose k hat for p. So step 2 is to figure out what the projection of this looks like. So this is just a plane that's going to be intercepting the xy plane when z is equal to 0. So you can substitute in z is equal to 0 and find out the equation where it intercepts. Let's just do straight line for that. This ends up being y is equal to -3 over 2 x plus 3. So this is where it intercepts. And then we can test some points and figure out that this is the region that is above z equals 0. This is 0, 2, and 3. So this is our region R, this triangle right here. So step 3. The gradient of G is 3, 2, 1. Remember, these are the x derivative, the y derivative, and the z derivative of our G function. The magnitude of the gradient of G is therefore the square root of 9 plus 4 plus 1. Or the square root of 14. So now we're looking at the dot product between the gradient of G and this k hat. Remember, because this is what we set for our P. We're going in the z direction for our projection. That means we're just looking at the z component here. So that's the magnitude of 1, which is just 1. For step 4, we would have to eliminate any z's that show up. So remember, we're just looking at for the surface area. We're not doing a surface area integral over maybe a density or something like that. So if we're just trying to find the surface area, our integrand is just 1. So there's no z's that show up. In our integrand, so we don't have to worry about step 4. For step 5, we can finally say that our surface area integral, so we're just calculating the surface area with an integrand of 1, is therefore the area integral over the region R of the magnitude of the gradient of G our conversion from ds to dA. And then we can go ahead and substitute in these quantities that we found. So we'll worry about the bounds in a second here for the area integral. But this is the square root of 14. This we found to be 1. So it looks like we just have square root of 14. And I'm going to do dy dx for this triangle. So y goes from 0 out to that hypotenuse, which was described as -3/2 x plus 3. And then dx was going from 0 to 2. Can you repeat why we don't have to worry about step 4? Okay, so notice in step 5 that there are no z's that show up, right? So maybe when I did the magnitude of this gradient, or I had some f function in here, there was a z that would come out. And notice that we're only integrating with y and x, so we would have to worry about z's, right? So if there was a z, we could use our g function to eliminate that. But for this case, there's no z's that show up in our integrand, so we're good to go. Okay, so now we just integrate this. Just going to pull out that square root of 14. Integral from 0 to 2. Negative 3/2 x plus 3 dx. Square root of 14. Negative 3/4 x squared plus 3x. X equals 0. X equals 2. Or 3 root 14. Perfect. This is our first surface area integral. So the steps just kind of help you keep track of, okay, I need to know where I'm projecting to, what does my projection look like? Let's go ahead and calculate the required transformation from ds to dA, and then eliminate any variables that aren't necessary or restricting in our integrands. And then we just do our area integral, which we should have a lot of practice with by now. Okay, so let's do another example. I'm going to do a lot of examples for this section. So determine the surface area of z equals x times y that lies in the cylinder x squared plus y squared is equal to 1. Okay, so here it's important to figure out what our surface is and what the constraint is. What is the region that we're talking about here? So a common mix-up that I see is that people don't necessarily know what to put as G because they think that G necessarily has to have the bounds kind of the bound information incorporated with it. That's not true. The projection is what defines our bounds. The surface that is defining the thing that is being projected doesn't necessarily need to stop at a given thing, right? So look at this function here. This is going to end up being our G function, but we're cutting it using the cylinder. So even though this thing extends past the cylinder, this is what defines our G. I don't care that it extends past the cylinder because the cylinder will give me the projection. The projection is defined by the thing that slices this G function here. Right? So I don't care that this keeps going. So we need this to equal to some constant. That's not too hard. We can just subtract one of these quantities over and set it equal to 0. So I'm going to say that G of x, y, and z is equal to x times y minus z is equal to 0. Right now it's equal to some constant, and we've got our G function here. Okay. Step 1. So our function, the original surface, was z is equal to x times y. I know this to be a function, right? A function means that for any one xy pairing, I only have one value of z, right? Just like functions in R2, right? Functions of one variable, right? If I plug in any unique xy coordinate, I only get one z that comes out of that. So that means that I probably want to project to the xy plane, right? Because this is a surface that might, look something like, the thing that we've drawn all the way up here. Doesn't necessarily look exactly like this, but this is a function of x and y. So that's very common for us to project to the x and y plane. So that will give us some idea of where to project to. It might not always be the case that we project to the xy plane, but because this can be written as a function of x and y, I'm going to choose to go in the z direction. So P will give us k hat. Okay. So what does our projection look like? So notice that the function g doesn't tell us what the projection looks like. It doesn't actually give us any information, right? Because for any x and y, it has some value in z. The thing that's cutting this surface to give us our bounds is the cylinder, right? It has to lie inside the cylinder. So x squared plus y squared is equal to 1. And this is another good reason why we chose to project to the xy plane, because our bounds are specifically in x and y. So this is just the unit circle, and this gives us the projection of just some circle of radius 1 here, centered at the origin. And this is our region R. So I see this circle, and I hope you all think the same thing. If I was doing this problem, this is what I would write on the side. Maybe polar. I'm going to have to integrate over this region R. This is a circle. Maybe I'll use polar coordinates if my integrand is relatively nice. Because remember, these are area integrals still. We can use either Cartesian or polar coordinates for that. So, step 3. The gradient of g is therefore y, x, -1. So the magnitude of the gradient of g is y squared plus x squared plus 1. If I wanted to use polar coordinates, maybe I would go ahead and convert that now. This is equal to r squared plus 1. Just in case we want to use it. Let's see what it looks like in polar coordinates. Then for the denominator, we're going in the k hat direction again. So this gives us the absolute value of the z component, which is -1, or just 1. Okay, so now for step 4, I look at my integrand. Now we're doing the surface area again. We're not integrating over a specific function, like we don't have a density or anything like that. So our integrand is 1 ds, and then its conversion using the steps from here in step 3. This doesn't have any z's in it. This doesn't have any z's in it. So there's no z's. So I don't need to worry about this step again. So now for step 5, our surface area given by the surface area integral with integrand 1. This will give us the area integral over the region R. We translate to the area integral here. And I think I'm going to try polar coordinates. It doesn't look like this integrand is going to give me too much trouble if I do polar coordinates, so we can go ahead and write it. So we have our double integral. Our integrand becomes the square root of r squared plus 1 over 1. So we just get this. Now remember, we're still doing polar coordinates. So this means we get this extra r here. That's our Jacobian, remember? So we have dr d theta. This is just a unit circle. So we go from 0 to 1 and 0 to 2 pi. We can do a u substitution here to do this integration. We can say that u is equal to r squared plus 1. So du is 2r dr, or that r dr is equal to 1/2 du. See, there we have our r dr. So we can rewrite this 0 to 2 pi. And then we have to do our u integral. If r is 0, u is 1. And if r is 1, then u is 2. Then we have our 1/2 square root of u du d theta. Or 0 to 2 pi, 1/2 times 2/3 u to the 3/2, evaluated when u is equal to 1 and u is equal to 2, d theta, or the integral from 0 to 2 pi of 1/3 2 to the 3/2 minus 1 d theta, or 2 pi over 3 2 to the 3/2 minus 1. So this just goes to show us that when we convert to the area integral from the surface area integral, we can still use polar coordinates. We can still use a different coordinate system. We just have to remember to do our Jacobians. So here we had the unit circle. We're like, oh, polar coordinates. Maybe we just double check. So it's worth noting that you don't, if you want to use polar coordinates, you don't translate this yet. You keep doing everything you would do in Cartesian coordinates until after step 3. So after step 3, once you take your gradient and your magnitude with this gradient in here, then you can translate to polar coordinates. We have not discussed how to do gradients in polar coordinates, nor will we. You can look it up if you want. The differential operator for the del here is different for each coordinate system, but it's pretty simple for Cartesian. It's just, partial x, partial y, partial z, and so on. But it is different in different coordinate systems if you want to take a look at that. But most of the time it's easier to just do in Cartesian and then translate back. Okay, so let's figure out where that transformation is coming from. Okay, so let's look at how ds relates to dA. Right, we've done these examples. We've kind of seen that it's pretty simple, but let's dive into the underlying mathematics. Where did I come up with that? Did I just pull it out of nowhere? So if we have some kind of transformation taken from ds to dA, what we're going to do first is observe. Oh, here we go. Oh, that is not what I wanted. I wanted a straight line. There you go. So imagine if we zoomed in far enough to the little small segment. It looked maybe something like this, just like a little surface segment. If we zoom in close enough, it looks relatively flat. And if we keep zooming and zooming in, it's going to look more and more flat. So down here, we have some area we'll call delta A sub k. And then here we have delta S sub k. And the idea here is, given some corner piece of this surface area, we have two vectors. This is very similar to our transformation argument. We have some vectors that kind of point to the ends of these surfaces. We'll call this UK and VK. At this point here, we also have some vector that defines the gradient of G at that location. We also have some vector that's pointed opposite to, or in the direction of the projection, which is our P. So now, using all of this, how do we kind of formulate what the surface area here approximately is in relation to our area down here, its projection? And of course, if we add up enough of these approximations in a sum, we end up with, some good approximation once we take a limit, and then we end up with the integral. So the idea is here, how do we approximate that surface area? What we're going to do is look at the area of the parallelogram. That's formed by the vectors UK and VK. So UK and VK kind of go to the edges of these points here. So maybe this isn't the best representation of that vector, because it'll end up kind of more like this. It ends up pointing directly at the edge of the surface. So it might skip over a little bit here, but it doesn't matter. We're just using an approximation. So remember, the area of that parallelogram, we can write as the magnitude of the cross product between these two. That's jumping back all the way to the first segment of this class again, right? The area of this parallelogram is the magnitude of their cross product. So then how does this translate to our delta AK? So if we go ahead and project that parallelogram down to the coordinate plane that we're taking a look at. So we have to look at the parallelogram that's kind of formed by the projection here. So we're going to use the triple scalar product here. So if you recall, what we'll do is the scalar triple product like this. And why this works is normally this would calculate some volume. But remember, the p vector is always going to be chosen as a unit vector that's going in the direction of the projection, right? So if this has a length of 1, the volume that's generated here will be the area of the projection of this guy here. So what we could do is instead write this as using cross product rules. I'm going to fill in that angle in a second here. So the angle between these two vectors, because remember, this is just using dot product rules here. We have the magnitude of the first thing times the magnitude of the second thing times the angle between those. So UK cross VK will have some angle, so some vector that just kind of pops off here. And we need to find out the angle between these two things. We'll call that gamma k. So some angle between these vectors. So this has a length of 1. This here, we already said, was approximately the surface area. And then all that's left is the magnitude of this, not y, gamma, of this angle, gamma k. Okay, so the idea is we need to figure out what this thing is, because this directly impacts the relationship between the area and the surface area. Why don't we actually pick up the rest of this proof tomorrow, because Heather and Teddy are in, and I went a little bit over. So why don't we take our 5-minute break here, and then we will continue tomorrow.